So let's start by thinking about how we can react with a reactive metal. And what do we know about what happens with water? What happens if I react a reactive metal, or if I put a reactive metal, and here I'm talking about, like sodium or potassium. What happens if I put reactive metal into water?
It reacts very.
What does it produce?
Gas.
Oh, yeah.
Yeah.
What kind of gas?
Hydrogen.
Hydrogen. This is a reaction from Phys-Sci that you must remember. It's not on the formula sheet anymore. What's our other product? Sodium hydroxide. Okay, this whole reaction needs to be on your formula sheet. So this is not balanced, is it? What do I need to do? Two for where?
Choose water.
Is that balanced now?
Yeah.
Okay. So the way I like to think about this reaction is if we focus in on the water, what's happening here? I can write the water like that. So all I'm doing is looking in close up at, actually I should have it this way around, shouldn't I? I'm focused in on that one bond there. Because what is happening when I react with the sodium is I'm breaking that bond. And if I've got two of them, and I break those bonds, then I'm able to have these two hydrogens head off to form hydrogen gas. And then that leaves these as hydroxide ions. Does that sort of make sense? Can you sort of see that that's what's happening? The sodium is ripping the hydrogen off the water. So if we think about what's going to happen with our oxidation of, not oxidation, if we're going to react now our metal with our alcohol. So we're comparing this, so we reacted that with water, just to remind ourselves of what happens in water. Now what's going to happen with an alcohol? Here, we're going to represent the carbon chain that's not part of the functional group with the letter R. And then we're going to say, okay, we've got that OH sticking out of our alcohol, and I'm going to react it with the sodium. And just like the sodium ripped the hydrogen off the water, it's going to rip the hydrogen off the alcohol. Now to balance it, we actually need two of these. And the booklet's wrong. So I'm looking at page 34, and the equation is not balanced correctly. It's got the 2 here, and 2 here, and 2 here, and then it says it's a half here, but it's not. Okay, we've got 2 hydrogens that have been released, because this is what's happened with right, so we've ripped off these 2 hydrogens to form H2 gas. And then what we're left with is our remaining carbon compound. Notice now, though, that this is an ionic bond. The sodium can't form a covalent bond.
Do you have to write it that way?
Yes. So we generally, if we were writing an ionic compound normally, we would put the positively charged ion first, but we don't do that now. We are going to indicate where it is on the molecule, and it's going to be at the end of the molecule by and large in this sort of situation. And we must also remember to include the charges on there to indicate that it is an ionic bond. Now, all of our alcohols will react this way. So, just like water, our alcohols react with a reactive metal to form hydrogen gas. And if you look on your formula sheets, you can also find this reaction. Let's write down the bottom there. Oh. I've got it's off to the side actually. It says alcohol in the middle and active metal, for example sodium, forms the alkoxide and hydrogen. Primary alcohols will react faster than secondary alcohols. And secondary react faster than tertiary alcohols. So in order of reactivity, we've got primary, secondary, tertiary. Now, having said that they react faster, that this is the reaction order, water is still much faster than the alcohols. So if we were comparing it against water, we would say this is the fastest, and then the primary alcohol, and then the secondary, and then the tertiary. But often you're only asked to compare within the alcohols. Why do you think this is? Why is it more reactive? Why is the primary alcohol more reactive?
It's the less bonds.
Sorry?
Why is less bonds?
No, we're going to be breaking the same number of bonds. Yes, Georgie?
Because the alcohols only have one.
That's it, yep. So it's all to do with symmetry, if you like, or the availability of that functional group to collide with another functional group. It's easier on the end than it is in the middle. Okay. So we just need to remember that reasoning applies for our functional groups all the time. It's the position that's going to impact on the reactivity. Okay, there are some questions for you to do on page 34.